So welcome to this lecture of analog microelectronic circuits. We were discussing about differential amplifier, and today we'll continue with differential amplifier, and we will see a typical differential amplifier, the disadvantages of that, and why we need to go ahead or why we need to have some modified version of the same differential amplifier. The ultimate target application what we are looking for is a kind of amplifier which can be used for instrumentation purposes. Instrumentation purpose, the meaning is the amplifiers which can be used for amplifying the biomedical signals, especially ECG, EEG waveforms. I hope you have heard about instrumentation amplifier. The intention of this lecture is to start with this differential amplifier and go up to different instrumentation amplifier. Alright. So as we have seen the characteristic equation of differential amplifier as this, where output is expressed as AD/VID plus ACM VCM, and what we are looking for is a very low common mode gain, or common mode gain should be ideally equal to 0, so that all the common mode signals will be rejected by the circuit. So when we say common mode gain will be equal to 0, that will really help in cancelling out all the noise and other disturbances which will most of the time which will appear in common to the input signals, and the differential gain should be high enough so that the differential input what is available at the input terminals can be amplified. Alright, so this is how we define the characteristic equation of this differential amplifier. So to continue with that, let us see how we can arrive at the architecture of a differential amplifier. So far we have discussed two types of amplifiers. One is inverting and another one is non-inverting. So far we discussed two amplifier configurations using Opamp. One is inverting amplifier, where we have the circuit of this type, where we this is how we connect a differential amplifier. So this is V in, this is V out, this is R1 and R2. This is inverting amplifier, and the other configuration what we learned is non-inverting amplifier, where this is how we provide input to a non-inverting amplifier. This is V in, V out, this is R1 and this is R2. Right. Now the need now is a differential amplifier which can accept two input signals. Two input signals. So but if you look at inverting and non-inverting individually, this can accept only one input here, this can accept only one input here. Now when you say we need to amplify the difference between two signals, what is expected is the amplifier should be able to accept two input signals, right? So there are different ways of looking at that. So if you look at the gain of this gain is minus R2 by R1, and the gain of this amplifier is 1 plus R2 by R1. Now the moment we say we want a differential amplifier which can provide amplification to different signals, one way is actually to combine these two and come up with a new architecture in the sense, by combining these two we can come up with an architecture which can definitely amplify the difference between two signals, right? Now when you combine, say if I am combining inverting and non-inverting, for inverting amplifier the gain is minus R2 by R1, but for non-inverting amplifier the gain is 1 plus R2 by R1, so which cannot be directly combined. So if I directly combine this inverting and non-inverting, the gain for the inverting path and non-inverting path both are different, right? So when I combine inverting non-inverting, then I should do something so that both paths will have equal gain. Are you guys following what I am trying to say? So say for example, if the inverting gain is minus R2 by R1, non-inverting gain also should be made as, so this also should be made as R2 by R1, right? So the gain magnitude should be made equal. So that is the so when I go ahead with a differential amplifier out of this inverting and non-inverting, the intention is, after making the gain of non-inverting amplifier exactly, the magnitude exactly equal to that of inverting, I can combine these two. Alright, so I'll tell you what I meant by combining these two. So the popular architecture of this non-inverting amplifier is like this, where you have a single op-amp, where one input is provided to the non-inverting terminal in the way what we configure in a inverting amplifier, this way. And the other input, generally see, if I am connecting in this fashion and say this is R2, this is R1, and if this is, I am calling it as input 1 and this as input 2. Now if I do in this way, what happens here is Vi1, the signal at Vi1 will have a gain equal to minus R2 by R1, and the signal at Vi2 will have a gain equal to 1 plus R2 by R1. So how will you find that? Since you have two signals, you can apply superposition theorem, and while applying superposition theorem, I will short this node Vi2 first, then we will know that Vi1 will have a gain of minus R2 by R1. And similarly, when I short Vi1 and check for the gain for Vi2, I'll get to know that it is 1 plus R2 by R1, which are not equal, right? So one modification we will do to this main circuit, and I'm just showing the modification using a different color. Instead of keeping this, instead of connecting Vi2 directly to this, or in order to make the gain of non-inverting amplifier also equal to this inverting amplifier, the idea here is add two more resistors. Instead of directly connecting this here, add two resistors. Let me mark this as R3 and R4, and we'll give signal here as Vi2. Right. So what we did here is we actually combined both inverting and non-inverting amplifier to get this difference amplifier or differential amplifier. So this is identified as a differential amplifier circuit. Right. Now I stated that the non-inverting and inverting path gain are made equal by adding the resistance R3 and R4. Now let us see how that is made equal. Right. So to check that or to make that equal, we should see, like we will see what has to be done in order to make those two gains equal, right? So you can see that clearly, you can see that there are two inputs here, Vi1 and Vi2. What I will do is I'll apply superposition theorem and analyze the effect of one input at a time to the circuit, right? So what I'll do first is let me assume that Vi1, let me short Vi1 equal to 0, because anyway for Vi1 we know that the gain is minus R2 by R1. Only difference is, or only thing what I need to check is for Vi2 what is the gain, right? So for that I am just shorting Vi1 equal to 0. And are you guys with me? Can I get some response in the chat? Vi1 is equal to 0. And alright, so after making Vi1 equal to 0, I'll draw the rest of the diagram here. So this is here, this is made equal to 0. We have another resistance here. So this is R1, this is R2, and we have R3 and R4 here. This is Vi2, this is R3, and this is R4. All right. Now, if I look at the non-inverting path, so non-inverting path is this. Now, if I look at the non-inverting path, what is the gain now? So if I write V out by V in, can you tell me what is the gain now? Previously, when in the absence of R3 and R4, the gain is equal to 1 plus R2 by R1, that we know, right? So V out is equal to V in into 1 plus R2 by R1. But now, let me write this as Vi2. But now it is not 1 plus R2 by R1, because if we are applying Vi2 to this node, and what is the voltage coming at this point? This point what I am getting is Vi2 into R4 divided by R3 plus R4. This is the actual voltage coming at this node, and that node voltage multiplied by 1 plus R2 by R1 is the gain. Is this clear? Now look at the circuit. What I have done is, if you look at the circuit, the only difference is, this is a non-inverting amplifier, but the only difference is you have an additional R3 and R4. So in the absence of R3, R4, the gain is equal to 1 plus R2 by R1. But in the presence of R3, R4, the voltage VI2 will be divided and the voltage available at this point will be equal to VI2 into R4 by R3 plus R4. Alright, so how I can write the gain now? The gain can be written as this into R4 divided by R3 plus R4. Now this is the gain of this non-inverting path, right? Now what I want to do here, I want to make the non-inverting gain equal to inverting gain, right? So what is non-inverting gain? Non-inverting gain is 1 plus R2 by R1 into R4 divided by R3 plus R4. This is non-inverting gain. And what I want to do here is, I want to make this gain equal to R2 by R1. That is the condition, right? So if I can make this non-inverting gain equal to R2 by R1, the inverting gain is already minus R2 by R1, so that I can consider this as a differential amplifier where the circuit can provide equal gain magnitude for both the signals appearing at the input, right? So now I don't know whether you are getting the question, why is it not possible even without adding an R3 and R4? It is not possible because now with the help of R3 and R4 we are actually trying, or we are looking for some condition which can force the gain equal to R2 by R1. That is what I have done here, right? 1 plus R2 by R1 into R4 by R3 plus R4 should be made equal to R2 by R1, and that is possible by choosing appropriate values for R3 and R4. Let us see how we can do that. So this can be written as R1 plus R2 divided by R1 into R4 by R3 plus R4 equals R2 by R1, right? Now here you can cancel R1 and R1. So what is remaining? The remaining term is R4 by R3 plus R4 here, and I keep R2 here and I will bring R1 by R1 plus R2 on the other side, right? So R4 by R3 plus R4 is equal to R2 by R1 plus R2, right? Further you can simplify, and finally you can come up with this, or I'll just take the inverse of this. So R3 plus R4 divided by R4 is equal to R1 plus R2 divided by R2. Now if I split, I can write it as 1 plus R3 by R4 is equal to 1 plus R1 by R2, or the condition what I need to force here is, if your R3 by R4 is equal to R1 by R2, I can say that the non-inverting gain will be equal to R2 by R1. Is it clear? Or little more clear? So this is the condition, or if I force the condition, if your R3 is equal to R1 and R4 equals R2, then I can say non-inverting gain will be equal to R2 by R1. So this is what the takeaway from this. Is this clear? Can I get some response in the chat? I'll explain this again. What I have done is, I want to make a differential amplifier which can provide equal gain to both the inputs, both the input terminals. So for that, so the question is, why do we want inverting and non-inverting gain to be equal? See, I have a signal and I'm applying a signal. I have two input signals and I'm applying that to an amplifier circuit. Now for one input, so generally when we look for an amplifier, especially differential amplifier, the amplifier should respond to the difference. Amplifier should amplify the difference of the input signal. But now one input I am giving to inverting terminal, another input I am giving to non-inverting terminal. Now if it is not having equal gain, both the signals are actually amplified by different factors, which is not generally what we do, right? Because we need to amplify the difference with an amplification factor, and that cannot be different, right? Now, so in order to make it equal, so whatever is the input signal coming in, both the paths, inverting and non-inverting paths, should provide equal gain. So in order to make equal gain, and since I have no other option to change or enforce a condition, what I have done is, we have added two resistors here, R3 and R4. Then after that, what I have done, So this remains the first input, and this remains second input. So for the first input, the gain is minus R2 by R1. For the second input, what is the gain? In order to study that, I have applied Vi1 is equal to 0. So the equation will reduce to this, and here I can write the gain. So without this term, the gain is equal to 1 plus R2 by R1 if I am directly applying the signal here. But since I am applying the signal through a resistive network, this division part also will come here. That is why we have this additional R4 by R3 plus R4. This as the gain. Now the need here is both inverting and non-inverting path should have equal gain. So since this is a gain expression for the non-inverting path, I am making this equal, I am forcing this gain equal to R2 by R1, and now that can be done by choosing appropriate value for R3 and R4. And what are those values? If R3 is equal to R1 and R4 is equal to R2, the non-inverting gain will be equal to R2 by R1. Alright, I hope this is clear. So what we will do now is, look at this. So now we made Vi1 equal to 0, and then we have evaluated and we got the gain expression. What is the gain expression? R2 by R1 into this difference. So similarly, if I make, I'll just do the checking of the other one. So if I am doing Vi2 equal to 0, then the circuit will remain as this, minus plus. You have this resistance here which is R4, another resistance here which is R3, this is R3, but now that is grounded, so there is no effect. Right, this is R2, this is R1, and this is Vi1, and this is Vout. Right, so here I can write Vout by Vi1 is equal to minus R2 by R1. Right, and in the previous case I can write Vout by Vi2 is equal to, what is the condition? Vi2 is equal to 1 plus R2 by R1 into R4 by R3 plus R4. Now what is the condition we have to do? R3 should be made equal to R1, and if R3 equals R1 and R4 equals R2, what happens to this gain? Vout by Vi2 becomes 1 plus R2 by R1 into R2 divided by R1 plus R2. Right. So this is equal to R1 plus R2 by R1 into R2 by R1 plus R2, which is equal to R2 by R1. Alright. So I can write Vout by Vi1 is minus R1 by R2, and similarly here Vout by Vi2 is equal to R2 by R1. Is this clear? Now if I have Vout by Vi1 and Vout by Vi2, what I need here is differential amplifier. So how will I write the differential amplifier? The output can be written as, Vout can be written as minus R2 by R1 into Vi1 plus R2 by R1 into Vi2. Right, or I can write V0 is equal to R2 by R1 into Vi2 minus Vi1, or this can be further written as R2 by R1 into VID, which is the differential input will be magnified by the value R2 by R1. Is this clear? Can I get some response in the chat? Yeah. Some more response. Alright, so now what is the circuit we have here? The circuit what we have as differential amplifier is an Opamp, this is a circuit diagram. So this is Vi1, this is Vi2, this is R2, this is R1, this is also R1, and this is R2, or you can write this is this is R3 which should be equal to R1 and R2 which should be equal to R4, and this is V out. This is the circuit diagram of a differential amplifier. So this is differential or difference amplifier. Right. So what we have written here as V0 by VID, this V0 by VID is nothing but differential gain of AD, and that value is equal to R2 by R1. Now the magnitude of differential gain is purely depending on the resistance value R1 and R2. So naturally R2 should be high and R1 should be low in order to have a very large differential gain. Right. So since this is differential amplifier and we are interested to know what is the common mode gain, because the expected common mode gain of the circuit is very low. Right. So we will quickly see how the what is the common mode gain of this circuit. So just wanted to know the common mode gain of the circuit. So I have just taken the same circuit over here, and let me put this as R3 and this as R4. Right. Now for common mode gain, the difference is what I have to do here is I will not have individual inputs like this. What I want to know is how the circuit will respond to a common signal which is appearing in common for both the signals, both the input terminals. So I am shorting these two and I am connecting a common signal, and I am calling it as say VICM, which is common. And even though we are connecting this as VICM, as when your common mode gain is equal to 0, the meaning is whatever is the signal which is appearing common to both the input signals will be, the effect of those input signals will be nullified. Right. Now this is how we have to find the common mode gain. So common mode gain is ACM, which can be obtained as V out by VICM. Right. So what I need to do is I need to write the expression for V out in terms of VICM in order to get the expression for common mode gain. So what I can do is, first let me just write what is the, because this is negative feedback, and if I am considering the open loop gain as infinity, that is what we have considered in all these cases. The open loop gain of Opamp is infinity. I am considering the Opamp as ideal as possible. Now what is the voltage coming at this node? This node voltage is, if I am providing VICM, that VICM into R4 by R3 by R4 is the voltage which is coming at this node. Right. Now by virtual ground I can say that even this node is also at the same potential. Right. These two are shorted and it is connected to VICM, and this node can be directly written in terms of R3 and R4. By virtual ground or virtual short, this node is also at the same potential, which is VICM into R4 by R3 plus R4. Right. Now if I want to write V out, I can write in two ways. One is, I know what is this node voltage. This node voltage minus the drop across this can be written as V out. Right. So how is that possible? Say when I connect this to VICM, say this terminal is carrying a current, and say that current is I1. That current cannot flow to this this node, this input terminal. So this current has to flow through this R2 only. So I can write V out as V out can be written as, so V out can be written as this node voltage. Let me just consider that node voltage as VICM into R4 by R3 plus R4, this node voltage, minus the current flowing here. The current flowing here is I1 into R2. This is how I can write V out. There are different ways we can write. This is one way to write V out. Right. So this V out is this node voltage. This node voltage is actually this node voltage minus the drop across this. Right. Now how can I write I1? What is I1? I1 is the current flowing through R1. So current flowing through R1 is same as current flowing through R2. So what is current flowing through R1? This node voltage is VICM and this node voltage is VICM into R4 by R3 plus R4. So I can write I1 as VICM minus VICM into R4 by R3 plus R4, or this can be further written as R3 plus R4 into VICM minus VICM into R4 divided by R3 plus R4. This is current I1. Now one term will get cancelled, so it is R3 by R3 plus R4 into VICM is the current. Now if this is the current flowing through this, I can write Vout can be written as VICM into R4 by R3 plus R4 minus R3 by R3 plus R4 into VICM into R2. This is how you will get, right? Vout is equal to VICM into this quantity minus this quantity. What I have done is I have just rewritten this expression again here. Now from this I can take this VICM common, or alright, so we will write in a different way so that we can directly apply and see. So Vout can be written as, if I take R4 by R3 plus R4 common, if I keep this as the common, the first term is VICM minus R3 plus R4 I have taken, so R4 is not there, so R3 will be here and I need to add one extra R4 in the denominator. And oh, did I miss something? Alright, yeah, I think I missed something here. So what is this current I1? Current I1 is this node voltage VICM minus this node voltage divided by R1. That I haven't done, right? This is only the voltage difference. This divided by R1 I should do, right? Are you getting this? So I have just written I1 as the voltage difference. The voltage difference divided by the resistance. I should add even that. So R1 should be added. So in that case, I'll have one more term here in the denominator as R1. So R1 is there in the denominator. Are you guys with me?
Yes.
Alright, yeah. So this is R1. So where I should add this VICM. Yeah. So there is one R1 term here. So this is VICM into R3 by R4 into R2 by R1 also will be here into VICM. This is the output expression, right? So if I write this further, I can write this as ACM. What is ACM? Common mode gain, which is equal to Vout divided by VICM, which is equal to R4 by R3 plus R4 into 1 minus R3 by R4 into R2 by R1, right? This is the common mode gain, right? Now for the differential amplifier, yeah, Sanket, I didn't get, yeah, I'll come back. So for this common mode gain, you can see that, no, this is the expression for common mode gain, and the previous condition what we enforced for differential gain is your R3 should be equal to R1 and R4 should be equal to R2. If I have this condition, by substituting this back to this will give you an ACM value which is equal to 0, right? So when your R3 equals R1 and R4 equals R2, your common mode gain will be equal to 0, and that is what we needed also, right? Because common mode gain should be as low as possible or it should be equal to 0, and that is possible with this. Alright, so the common mode gain is equal to 0. So this is your 0 volt. Now one problem or one thing what you can see here is common mode gain will be equal to 0 only if your R3 equal to R1 and R4 equal to R2, or I can say any mismatch in the resistance values, which is possible because it is not practically possible to have two resistors of equal value, because at least tolerance there will be some difference. So any mismatch in resistance in R values can give a non-zero common mode gain, right? So whenever common mode gain is non-zero, that will lead to a finite common mode rejection ratio. So in practical cases we will only have finite common mode rejection ratio, we will not be able to have infinite, but the value of the common mode rejection ratio also matters, because the higher the CMRR, it is better, because if you are not having a higher CMRR, the circuit is prone to noise, is the inference from the circuit, right? So this is how a differential amplifier. So what we have done with this differential amplifier is we have looked at both the common mode gain and the differential gain, and we can say that common mode gain should be as low as possible and differential gain should be as high as possible, right? So that's all about this differential amplifier. If you have any questions on this, I can take it now.